Hello, my name is Rebecca Maynor, and this is my project number 2 based on rectangular integral fin tubes. The data was collected about fin tubes where the independent variable was the unflooded surface area ratio of the fin tube. The unflooded area is the area at the top of the fin tube where the condensation does not reach when the vapor goes into the tube. This is measured in millimeters, while the dependent variable, labeled here as heat, was the heat transfer enhancement. This was measured in watts because heat is a form of energy. This is a continuous variable. The x variable, or the unflooded surface area ratio, is also a continuous variable. What are fin tubes? That's a good question. These fin tubes are tubes, these pipes. In our instance, they are copper pipes, like the top picture, with these little bar-looking things coming off of them. Those are what are called the fins. In the top picture, there are kind of circular fins. In the bottom picture are rectangular fins. The rectangular fins are the ones that will be observed in this study. These fins increase the surface area of the pipes, enabling a better heat transfer for the job that is trying to be completed. So the data came from a group of people trying to study how the surface area of the unflooded section of the tubes impacts the heat transfer. You can kind of see the fins on this diagram here and how heat is transferred in these tubes, right? So they studied this data and tried to figure out the best way to optimize heat transfer based on the surface area at the top of the tube. What does the data look like? So this is our data. This is the ratio, or the surface area ratio, on the horizontal axis, and our heat transfer enhancement on the y-axis. These are 24 different data points collected in the study. Each tube was flooded with vapor to see how the heat transfer reacted based on the surface area. And the data was collected from these 24 different tubes, and their data is present here on this graph. What is the trend of the data? So when we plot this data, we can use R and create this nice looking graph that kind of shows us where the trend in the data is, how the data moves as we increase on our ratio line, right? So it's not a parabola or a line, it's just the general flow of the data. You can see it kind of curves up at the top a little bit on the right side because of the one data point that is lower. It doesn't seem to fit the trend as well. When we apply a straight line to it, a straight line trend, we can see what that would look like. So we're trying to determine if this data could be linear. And that is what this line represents. This is a line that could be a linear model of the data, and we are trying to determine if this is a fitting model for the data. What is my research question? So the original research was trying to optimize the heat transfer of these tubes, but what I'm trying to look at is the data that they collected in this heat transfer. If this heat transfer can be represented in a linear fashion. So I am not creating new research data, I am analyzing the data that they created and seeing if I can represent it in a linear fashion. So we are going to use simple linear regression to determine if a linear model can be used. So we have our model for linear regression, y equals beta naught plus beta 1 xi plus epsilon. Epsilon is the error. So when we take the expected value of y, we get the beta naught plus beta 1 xi. This is because the expected value of the errors is 0. We want the errors to align across 0. We want the mean of the errors to be 0 for our model to accurately represent the data. So the assumptions we make is that the trend of the variable is linear. So we can kind of see that in the previous slides, that the linearity of the data. The errors are independent of each other. The errors have a normal distribution with a mean of 0, which is what we just assumed previously, and the errors have a constant variance. So we can generate a linear model in R, and this is the linear model that was created. We can see the coefficients, the beta naught and beta 1 in this model, as well as the residual standard error in the R-squared value. So this model shows that the estimate of beta naught is 0.2134, and the estimate of beta I for a y value is 2.4264. Now we can see if these estimates are valid. So we do this by looking at the confidence interval for the estimates. We look at this 95% confidence interval to see if our beta naught and beta 1 are in these intervals. So the intercept shows that our beta naught, or 0.2134, is within that interval, and our slope, or beta 1, 2.4264, is in the interval as well. That interval is represented on the bottom. So what would it look like as a linear model? We kind of looked at this already. We put a trend line through these values and see what that looks like. And we use this through simple linear regression to minimize the distance between the line and each of the dots. We take that distance and we square it, and we try to minimize that value. What are the residuals? So the residuals is what we end up squaring. The residuals are the distance between each point and our estimated line. So you can see the formula for there, and the value we calculated for just the sum of those. Then we can also look at the means. The mean of each predicted y value. So if you collect a bunch of data for x equals 1, what are the mean values of the y's? And that's what that line represents, that line with the increasing slope. The horizontal line represents the mean of all of the data points now collected. We can see what those means are and see how those compare, and we can see the calculation for that at the bottom. We can also calculate how far the values deviate from that standard mean. So that's what the orange lines represent, and we can find that calculation at the bottom. The total deviation from the mean to the points are 27.805. What does this matter? So the R-squared value is what we look at to determine how linear the model is. So we get a pretty high R-squared value, 0.837409. The closer it is to 1, the better it can be represented as a linear model. So this is sufficient for us to continue with our analysis. we can look at the errors created, so those residual values, and see how they are scattered and see if their mean is in fact 0, which is what we want. And so we plot these points and look at their trend line, and their trend line is around 0, which means the mean of this data is in fact 0. We can see that again here with another trend line representation. There's a slight curve down at the bottom. It's that same point that we were having issues with earlier, looking like it might not fit the data as well. But this is the errors. So that's a decent error. It's hovering around 0, so that's okay. We can accept that. So now we have to look at the distribution of these areas. We want the distribution to be normal, and so we generate graphs for these areas and perform a test. The hypothesis for this test is that it is a normal distribution, and we can see that the p-value is 0.806, which means we do not have enough evidence to reject our idea that the distribution is in fact normal. So we can go ahead and say that is normal. And now we've got most of our assumptions covered. We've shown that the trend line is roughly linear through the several different graphs. We've shown that the mean of the year, that it's distributed normally. And we can also say that the errors are independent because they do not depend, they are not affected by one another. So if you have an error for one x value, that has nothing to do with the error for a different x value. They're two separate trials, two separate situations, two separate types. So those do not affect one another, so the errors are also independent. Because they are independent and identically distributed, their variance will be the same. So this means there is a constant variance for all values of x, and we have covered all of our assumptions. So we can look at how our model that we have created represents the data performing predict test. So we take a few values of x, 2.12, 1.88, and 1.62, and we see what our model generates. And our model generates values fairly close to the actual values for our data. So we can see that the bottom line here are the actual values, and the top line represents the output or the predicted values. And those are relatively close to each other, which means we still can say that our model seems to be represented linearly in an appropriate fashion. So then we can perform the Cook's distance plot to see if there are any outlying variables that don't seem right, that maybe need to be looked at again or taken out of the data in order to create a better linear model. And so here we see the 16th observation seems to be not aligning with the rest of the observation. So we can go ahead and take that out to generate a new model that would probably give us a better understanding of the data and a better linear model or a better representation that's generated from that curve we saw at the beginning. So from all of this, we can conclude that for our data points that we have from that range of values, we can use a normal distribution to describe the errors, and that the errors have a standard variance of 0. This means that the model can be described linearly, and we can improve our model by using a quadratic representation rather than a linear representation from that curve, or we can take that curved part out and generate a straight line that represents our model. We'd have to do more investigation to determine what the best outcome would be for our model.